Have you ever stopped to think that the very air you breathe could hold a secret to like supercharging your energy from the inside out? I mean, it sounds almost too good to be true, right?
Right.
But today we're actually diving into the fascinating science
Yeah.
that suggests you might have way more control over your cellular energy than you'd think.
Yeah, that's right. And we know you're the kind of person who loves to get to the heart of these complex ideas quickly, without feeling overwhelmed. So we've done the heavy lifting. We've gone through a ton of research to bring you the most compelling stuff, the nuggets, if you will, on how this might actually work.
Exactly. So today we are taking a deep dive into this intriguing connection between electrical charges, those tiny sparks of energy, and the powerhouses inside our cells, the mitochondria. Imagine being able to tweak those tiny forces at a cellular level to essentially boost your fundamental energy source. That's the frontier we are exploring today.
Yeah, and we've looked at everything from, the initial sparks of this idea to more concrete proposals, and we're going to break it all down for you. So our mission today in this deep dive is to really understand the potential of what we're calling charge-modulated mitochondrial enhancement, what it is, how it might work in your body, and whether it's actually feasible. Could this actually become a reality?
Okay, so let's start with the basics. Everyone knows we get energy from our food, but where does that energy actually come from? It all boils down to these tiny structures inside our cells called mitochondria, the powerhouses of the cell. And they produce this energy, known as ATP, through an incredible process called the electron transport chain.
You got it. Think of the electron transport chain, or ETC, as like the core engine of energy production in your cells.
Right.
And it works by creating this sort of crucial difference in electrical charge, a proton gradient, across a membrane within the mitochondria. Imagine like a tiny dam holding back a flood of charged particles. This stored electrical potential is the key to how our cells make energy.
I see, like building up potential energy.
Exactly. And there are these critical players in this process, these protein complexes, numbered 1, 3, and 4. They're like the tiny pumps that push these charged particles across the membrane, creating that imbalance that powers the whole system.
Okay, so the big idea here is that we're looking at whether we can somehow influence this electrical imbalance, this charge differential, to make the whole energy-producing process more effective, right?
Right.
Like we're fine-tuning the flow of energy at its most basic level.
Exactly. And that brings us to some of the initial concepts scientists were exploring about how to actually influence this charge from the outside. Early ideas revolved around using external charge fields, either static or oscillating, to sort of nudge these charged particles across the cell membranes.
Okay, so are we talking about using pulse electromagnetic fields, those PEMFs you hear about, or even something called capacitive coupling?
Yeah, exactly. Those are some of the methods that were explored early on. It's like, imagine trying to subtly influence the flow of water in a pipe using magnets from the outside. You're not directly touching the water, but you're using a force to guide it.
I like that analogy. So using these forces to kind of nudge those charged particles in the right direction.
Precisely. Now, another interesting early approach focused on what they call surface charge coatings. The thinking here was, imagine you could coat surfaces, like, say, the lining of your lungs, with these tiny negatively charged nanoparticles.
I see.
So these minuscule particles would create this localized electrical gradient. And the hope was that the nearby cells, specifically the mitochondria within them, would sense and respond to this altered electrical environment.
Interesting. So kind of creating an environment where the mitochondria are encouraged to work more efficiently.
Yeah, that's the idea. And there was even discussion of using these ultra-low power effects similar to a very gentle form of electroporation. Not enough to damage the cell in any way, but just enough to perhaps make the cell membrane slightly more permeable to ions to allow for a bit more flow into the mitochondria.
So basically, we're trying to find that sweet spot, that Goldilocks zone, where the influence is strong enough to make a difference, but not so strong that it causes harm.
You got it. That's precisely the challenge highlighted in the research. Finding that sweet spot. Something that's stronger than the ambient ionization, but significantly weaker than something that would cause, direct electroporation.
It's a delicate balance, for sure. And that brings up a key question. Are we trying to influence the mitochondria directly, or are we going for a more broad, systemic change to the body's overall electrical state?
Yeah, that's an important distinction. Systemic approaches would involve trying to change the overall electrical environment of your body and hope that this trickles down to the mitochondria, while direct modulation focuses on targeting those tiny powerhouses specifically.
So if we talk about systemic approaches, what are some of the early ideas that researchers were tossing around? I've heard about inhaling ionized oxygen or even charged particles. The logic seems straightforward. Breathe in charged air, get an energy boost, right?
Well, it sounds simple on the surface, but the research points out a major roadblock here, and that's your body's incredible system for maintaining ion balance.
Right.
Think of like the sodium-potassium pump or all those exchangers that are constantly regulating the levels of sodium, hydrogen, and calcium inside and outside of your cells.
Right.
They work tirelessly to keep those ion concentrations within a very narrow range, effectively buffering against any drastic changes from the outside.
So our bodies are pretty good at maintaining homeostasis, even when we're trying to give them a little electrical nudge.
Exactly, and that's why some of those charge-enhanced antioxidants or structured water you hear about, while they sound appealing, lack the strong scientific evidence to back up their claims of significantly improving redox potential.
Redox potential, just a reminder, is essentially the balance of available electrons for energy production within your cells.
Right, and that balance is mainly governed by fundamental metabolic processes happen within the cell itself. So while external factors might play a small role, they don't seem to be the major drivers.
Makes sense. Now, the research did touch on pulsed electromagnetic fields, those PEMS, potentially having some subtle effects on cytochrome site oxidase, which is a key component in that electron transport chain we talked about earlier.
Right, but the effects seem to be very context-specific, like they might only occur when synchronized with your breathing patterns. It's a very nuanced area.
And of course, there's the issue of safety. Flooding the body with strong electrical fields, even if it did boost energy, could have some pretty nasty side effects, like damaging cell membranes or increasing those harmful reactive oxygen species, or even messing with your heart rhythm.
Absolutely. You always have to consider the potential downsides, and that's why a lot of the research has shifted towards more refined concepts that focus on this very targeted charge modulation.
So instead of a broad brush approach, we're now looking at more precise ways to apply electrical influences within the body.
Exactly. It's about finding the right target and the right level of influence. And this is where things get really interesting. There's this concept called dual-layer charge synchronization, which aims to tackle the challenge on two fronts, both at the level of the mitochondria themselves and more broadly in the system.
I like it, a two-pronged approach. So how does this work exactly?
So for the mitochondrial level, the idea is to use these piezoelectric nanoparticles. Now, these are incredibly tiny particles that can be attached to the surface of mitochondria using special targeting molecules, like those that bind to the TOM20 protein. It's like a specific address tag for mitochondria. And the cool thing is, these nanoparticles can convert mechanical energy, like the vibrations from your blood flow, into localized electric fields, right there at the mitochondrial membrane.
So the natural movement within your body could actually power these tiny electrical boosts where they're needed most.
Yeah, it's a very elegant way to utilize the body's own existing energy. Now, on the more systemic level, the proposal suggests using wearable devices that emit ions, like electrostatic patches applied to the skin. They could generate gentle charge fields, maybe synchronized with your breathing, to kind of prime the lungs and blood for a more effective uptake of, say, charged oxygen species.
So it's like setting the stage for enhanced energy production. And I've also heard about something called calcium charge coupling. How does the flow of calcium ions fit into this whole electrical picture?
Well, calcium plays a critical role in regulating how active the mitochondria are. Calcium ions can activate ATP synthase, the enzyme that actually makes ATP, and also influence other enzymes involved in those metabolic pathways that feed into the ETC. So the idea here is to use light to control the flow of calcium into the mitochondria, either through techniques like optogenetics or using these light-sensitive molecules called ionophores. And by precisely timing a boost of calcium into the mitochondria with the application of these external charge fields, you could potentially maximize ATP production and even prevent those energy-wasting proton leaks that we talked about earlier.
So we're talking about very fine-tuned control here. But how are scientists addressing the earlier challenges we discussed, like charge dissipation and the body's tendency to maintain its balance? How do these new approaches get around that?
Well, these more targeted methods address those issues directly. The piezoelectric nanoparticles, for example, they're generating those fields right at the mitochondria, minimizing that systemic loss of charge. And the use of these pulsatile charge fields, often in the 5 to 15 hertz range, is mimicking those natural electrical rhythms within your body. This might help avoid the body's resistance to change because it sees these signals as something familiar.
Okay, that makes sense. But we have to talk about safety. Are these newer concepts addressing the potential risks of messing around with electrical fields in the body?
Absolutely. Safety is paramount. The proposals emphasize using these very low-intensity fields, often at or below 1 volt per meter, which is considered to be below the threshold for causing major cellular changes. Additionally, some concepts include using antioxidant nanoparticles like cerium oxide, which can help neutralize any of those nasty reactive oxygen species that might be generated. And there's also this really interesting idea of modifying hemoglobin, the oxygen-carrying molecule in your blood, using inhaled iron nitrosyl complexes. This might improve oxygen delivery without any harmful side effects.
So we're seeing a move towards gentler, more targeted approaches,
Mhm.
and inhalation keeps coming up as a potential delivery method. What are some of the more advanced ideas being explored for using our breath to support mitochondrial function?
The thinking has gone way beyond just breathing in negative ions. Researchers are proposing advanced inhalation systems with special interfaces, almost like little chambers with embedded electrodes. These would create what some are calling charge gradient tunnels, essentially concentrating the charge as air travels towards the lining of your respiratory system.
Much more targeted than just generally increasing the ions in the air.
Exactly. And there's also this idea of delivering what are called biphasic pulses of ionization, synchronized with your breathing. So you alternate between negative and very subtle positive ion pulses. This might help to maintain the cell's responsiveness and avoid them getting used to a constant negative charge. And then there's the use of nanoaerosolized charge carriers, which are essentially tiny particles that can carry the charge more effectively. Things like hydrophilic nanoparticles, fulvic acid complexes, or biocompatible mineral suspensions.
These sound like some pretty high-tech solutions, but how do we get these charged particles past those biological barriers in the lungs and into the cells where they need to be, or even into the mitochondria themselves?
There are a few strategies researchers are looking at. One involves incorporating tiny amounts of phospholipids, or very mild surfactants, into those aerosols to temporarily increase the permeability of the respiratory lining, making it easier for those particles to get through. Certain compounds, like quercetin and resveratrol, which can interact with channels in cell membranes, might also play a role here. And for direct delivery to the mitochondria, researchers are looking at using something called mitochondrial targeting sequences, which are essentially short chains of amino acids that act like a zip code, guiding those particles specifically to the mitochondria. Even the timing of the exposure is being considered, aligning it with your natural circadian rhythms when your mitochondria might be more receptive.
Wow. The level of detail and thought going into this is incredible. We've also touched on some concepts that almost sound like they belong in the realm of quantum mechanics. What can you tell us about this quantum coherence enhancement?
This is where things get really theoretical. The idea is that by creating these highly ordered or coherent ion fields and using charge carriers like deuterium-depleted water vapor, which some believe has unique quantum properties, you might be able to enhance the efficiency of certain quantum biological processes happening inside the cell. It's all about achieving a more synchronized and efficient energy transfer at a subatomic level.
So we're not just trying to force charge into the system, we're also looking at these subtle biological cues and signals.
Exactly. It's about working with the body's natural processes, not just overriding them.
Now, we've talked a lot about directly delivering charge to the mitochondria, but there's also this idea of the respiratory lining itself acting as a kind of signaling interface. Can you explain that a bit more?
Yeah, this is really interesting. It's called the gaseous ion messenger complex concept, and it proposes that these stable clusters of ions can actually bind to naturally occurring signaling molecules in your body, like nitric oxide, hydrogen sulfide, and carbon monoxide. These complexes might then interact with the cells lining your respiratory system, setting off a chain reaction of signals that indirectly influence mitochondrial function throughout your body.
Fascinating. So the lungs aren't just a gateway for air, but also kind of sensor and communicator influencing energy production elsewhere.
Exactly. And some scientists even speculate that the lining of your lungs might have these specialized voltage-sensitive cells that connect to the vagus nerve, which we know is involved in regulating lots of bodily functions, including metabolism.
Right.
So, stimulating these cells with specific patterns of charge could potentially tweak the activity of mitochondria throughout your body through neural pathways. And there's even this, very theoretical idea of quantum biological signaling using coherent electromagnetic fields at the extremely high frequencies associated with electron movement within the mitochondria.
We're talking about cutting-edge stuff here.
This is all incredibly complex, but also really exciting. How might these advanced inhalation concepts be put into practice in a way that people could actually benefit from? Well, some practical ideas include dual-phase delivery systems.
Okay.
Imagine a device that first prepares the lining of your lungs and then delivers those specific charge carriers. There's also nasal-specific targeting, focusing on the olfactory epithelium in your nose, which has direct connections to the brain. And then there's this idea of charge pattern encoding, where the precise timing and pattern of charge delivery might be even more important than the overall amount of charge.
So it's not just about brute force, it's about finesse. And all of this leads to a very tangible concept, the idea of a device that harnesses negative ion charge dynamics for health and performance enhancement. Tell me about this neon bioenergizer concept.
So this concept imagines a device, maybe for your home or at the gym, that would have several key components working together.
Okay.
First, you'd have a high-output ionic generator, something that can produce a dense cloud of negative ions. Second, you'd have a respiratory optimization chamber. This would have controlled airflow and humidity to create that perfect environment for breathing in those ions. And third, some are suggesting a pulsed electromagnetic field generator to kind of amplify the cellular response to those ions.
So we're talking about creating a specific microenvironment to maximize those potential benefits, right?
You got it. It's not just about breathing in charged air. It's about creating the optimal conditions for your body to utilize those charges.
That makes sense. So what kind of variations might we see with a device like this?
Well, you could have a smaller, sleek desktop version designed for general wellness, maybe with 360-degree ion dispersion. And then you could have a larger, more robust gym or performance-oriented version with multiple directional outputs to create targeted training zones with enhanced air quality.
I like that, different versions for different needs.
Yeah.
And in terms of the user experience, what kind of features might this device have?
Well, it could have timed performance modes, tailored for pre-workout stimulation, post-exercise recovery, or even to improve mental focus.
Oh, nice.
And you could even integrate it with those wearable fitness trackers to personalize the ion exposure based on your activity level and how your body's responding. But of course, the big question is, would it actually work? What would scientists look at to test and validate a device like this?
That is the million-dollar question. What are the metrics that really matter?
Researchers would likely look at a range of physiological indicators. So in the short term, they might assess heart rate variability, the efficiency of oxygen utilization, or how quickly you recover after exertion. Cognitive tests could measure things like mental focus and reaction time. And in the long term, they would want to monitor those biomarkers of mitochondrial health in regular users, maybe through blood tests or other measures.
So a lot of different ways to measure those potential benefits. Taking a step back, why is all this talk about charge dynamics even relevant to our biology in the first place? What's the fundamental connection there?
Well, at the most basic level, all living cells maintain this resting electrical potential across their membranes. It's like a tiny battery. And by introducing these localized concentrations of negative ions, you can subtly influence these inherent cellular electric fields and the electrical gradients that exist across tissues.
It's like giving the body's natural electrical system a little nudge in the right direction.
Precisely. And the subtle nudge can then trigger these downstream signaling pathways that rely on electrical charges. For example, negative ions might activate these things called voltage-gated calcium channels, letting a little bit of calcium into the cells. And calcium can then act as a messenger, influencing key mitochondrial proteins, ultimately boosting the efficiency of that electron transport chain. Plus, those extra electrons from negative ions could shift the intracellular redox state towards a more balanced environment, which is really good for optimal ETC function and that healthy ratio of NAD plus to NADH. Even small changes in local pH due to those negative ions could contribute to a slightly enhanced proton motive force within the mitochondria.
This is really amazing stuff. We're basically talking about optimizing energy production at a fundamental level.
Yeah.
But despite all these exciting possibilities, there must still be some pretty significant challenges that need to be overcome.
Definitely. The biggest hurdles are still: how exactly are those inhaled charges transferred inside the cells? How do you ensure those ions remain stable before they get neutralized in the body? And most importantly, how do we get solid scientific data that directly links those inhaled ions to improvements in mitochondrial function? For example, we need better ways to actually measure that mitochondrial membrane potential in cells exposed to high concentrations of negative ions.
So we need more research, more data, and more precise measurement tools. And how can we be sure that we're creating this beneficial electrical environment without causing any unintended negative effects within the body?
That's a great question, and it all boils down to carefully designing these controlled charge environments that maximize the interaction with target cells while minimizing charge dissipation. Researchers are exploring things like oscillating charge fields at frequencies that resonate with the body's natural rhythms, and also investigating the potential of charge carrier enhancers like water vapor or structured water. Localized delivery methods that specifically target areas like the nose and skin, maybe integrated into breathing systems, might also be more effective and safer in the long run.
It sounds like we're still in the early stages of understanding all of this, but ultimately, to really know if any of this works in humans, we need rigorous clinical trials. What might those trials look like?
A phased approach would be essential. Phase 1 trials would primarily focus on safety and feasibility. Researchers would recruit healthy volunteers and carefully monitor things like reactive oxygen species levels, heart rate variability, brainwave activity through EEG, and ideally, look for any initial signs of improvement in mitochondrial membrane potential.
And if those initial safety trials look promising, what happens next?
Then things move to phase 2, which would involve recruiting people who might benefit most from these interventions, athletes, older adults, or people with metabolic conditions.
Okay.
These studies would be placebo-controlled, and they might use a crossover design to assess the impact on different performance metrics like physical endurance and cognitive function. They would also monitor those important biomarkers over a longer period, like NAD plus to NADH ratios, and the activation of key metabolic enzymes like AMPK. Some researchers are even talking about using fMRI to assess brain activity and oxygenation. It's getting very sophisticated.
And the ultimate goal would be phase 3 trials, right?
Okay.
Those large-scale studies to see if this really translates to real-world benefits.
Yeah.
What are some of the potential applications researchers are envisioning?
Well, in phase 3, they'd aim to show clinical efficacy for things like anti-aging interventions, optimizing athletic performance, or even treating those metabolic diseases linked to mitochondrial dysfunction. But before we get there, the immediate next steps are really about refining those specific parameters for the bioelectrical fields, getting the necessary approvals and funding, and actually building those functional prototypes of these devices.
So a lot of work ahead, but with potentially huge implications for human health and well-being. As we wrap up our deep dive today, what are the key takeaways you'd like our listeners to remember about this whole concept of charge-modulated mitochondrial enhancement?
The biggest takeaway is that there's this incredibly exciting possibility of influencing the fundamental way our cells produce energy, using carefully controlled electrical environments and interactions. We've talked about directly targeting mitochondria with nanoparticles, using our breath to deliver charge, and applying external charge fields. The core idea is that by precisely tweaking our own bioelectric landscape, we might be able to unlock a whole new level of mitochondrial function, and that could have profound implications for everything from how we age to how we perform physically and mentally.
This has been a truly mind-blowing discussion, and I have to admit it's given me a lot to think about. Considering just how fundamental charge dynamics are to our biology, what other ways might we be able to interact with and influence our own bioelectricity? It's a question that begs further exploration.
That's a fantastic question, and it speaks to the vast potential of this emerging field. Thank you so much for joining us on this deep dive. We hope we've given you a clear and engaging look at this complex topic and sparked some new insights for you to ponder. Until next time, keep those bioelectric sparks flying.
I love it. Keep those sparks flying.